Every year, around 700 aircraft worldwide make their final flight. Yet instead of becoming enormous piles of scrap, nearly 90% of their materials can be recovered, yielding tens of thousands of tons of valuable aluminum, steel, titanium, and specialized alloys. In this video, we will follow the rebirth of an aircraft, from draining its fuel and removing the engines and electronic systems, to cutting apart the fuselage, wings, and tail. Each type of metal is then sorted, shredded, melted down, and returned to the manufacturing chain. Stay with Factron Process to discover how a machine that once conquered the skies can continue to exist long after its final flight, in an entirely new form. Over the next 10 years, more than 200,000 tons of material from retired commercial aircraft will enter the recycling process. Hidden inside these machines, which once carried millions of passengers, is a vast urban mine filled with aerospace-grade aluminum, titanium, and high-value superalloys. One Finnair Airbus A319 alone yielded around 15 tons of aluminum, with an overall recycling rate of 99.2%. The metal recovered from this single aircraft helped avoid emissions equivalent to the annual output of 55 cars, showing that an aircraft's final flight can sometimes mark the beginning of a far more valuable second life. The first destination for many retired commercial aircraft is not a recycling plant, but a specialized storage center. After their final flight, aircraft are often transferred to facilities located in dry climates, where their airframes can be preserved for longer, while their owners decide whether to return them to service, dismantle them for parts, or send them for recycling. One of the largest storage networks in Europe is operated by Tarmac Aerosave. With facilities in France and Spain, its 3 sites can accommodate around 280 aircraft and 120 engines. Among them, Teruel, located on the dry high plains of Spain, has become a familiar destination for many commercial aircraft after their final flight. Once the aircraft lands, it is towed away from the active operating area and moved to a designated parking position. The airframes are arranged in rows with enough space for towing vehicles and technical crews to access them later. From this point, the aircraft officially leaves the air transport network and enters the first transitional stage of its end-of-life journey, awaiting assessment before proceeding to preservation, dismantling, or recycling. After entering the storage facility, the aircraft undergoes a comprehensive inspection before a decision is made to preserve it, remove usable components, or send it for recycling. The technical team first reviews the maintenance records, total flight hours, and the number of takeoff and landing cycles completed by each major component. Next, the fuselage, wings, landing gear, and other heavily loaded areas are examined for corrosion, cracks, or deformation. Hidden damage may be detected using ultrasonic testing, eddy current inspection, or bore scope cameras. Remarkably, the greatest value of a retired aircraft often lies not in the aluminum of its airframe, but in its engines, avionics, and thousands of components that may still be fit for service. Based on the inspection results, technicians create a value map, identifying which parts can return to flight, which require repair, and which will move on to recycling. Before an aircraft can be dismantled, all remaining fuel, lubricating oil, hydraulic fluid, and other technical chemicals must be drained from its systems. The fuel tanks, pipelines, and distribution lines are then cleaned to minimize the risk of fire or explosion during the cutting process. At the same time, technicians remove the batteries, fire extinguishers, oxygen cylinders, pressurized equipment, and any components that may contain hazardous materials. On older aircraft, insulation, protective coatings, and certain electronic components may also require separate handling in accordance with environmental regulations. This is a mandatory step before any cutting equipment or heavy machinery can approach the aircraft. Even a small amount of residual fuel or solvent vapor trapped inside a pipeline can turn the dismantling process into a serious safety hazard. Only after the aircraft has been fully decontaminated and certified safe is it ready for the removal of its most valuable components. Once the aircraft has been decontaminated, the dismantling team begins inside the passenger cabin. Seats, overhead bins, tray tables, carpets, partitions, service carts, and complete galley units are removed one by one from their mounting points. Components that remain in good condition are not shredded with the airframe. They are cleaned, tested for fire resistance, and sorted for resale to airlines and training centers, or converted into interior features for restaurants, hotels, or offices. At aviation-themed facilities, an approved aircraft seat in particular is far more complex than it appears. Its frame must be lightweight while still withstanding impact forces many times greater than the passenger's body weight. Stripping the cabin also allows aluminum, plastic, fabric, seat foam, and electrical wiring to be separated before the fuselage is cut apart. Within just a few days, a cabin that once carried hundreds of passengers can be completely emptied, exposing the metal structure and kilometers of wiring hidden behind its interior panels. Once all preparation stages are complete, the technical team begins removing the jet engines, the most valuable components on most commercial aircraft. First, the engine cowling panels are opened or removed to provide access to the internal systems. The fuel, hydraulic, electrical, and sensor connections are then disconnected before the engine is separated from its mounting pylon beneath the wing. Because a jet engine can weigh several tons, it cannot be lowered using ordinary equipment. Specialized lifting systems, cranes, and support stands are required to control the operation with extreme precision. Once on the ground, the engine is transported to a maintenance facility for inspection, overhaul, or disassembly so that serviceable components can be recovered. Only when it no longer meets aviation standards is it sent for metal recycling. The engines and their internal components account for a large share of the aircraft's remaining value. For this reason, engine removal is always one of the most carefully managed and economically valuable stages in the entire recycling process. After the engines, avionics, and entire cabin interior have been removed, only the aircraft's structural frame remains. Rather than destroying it immediately, the dismantling team cuts the fuselage, wings, and tail along carefully planned structural lines. This helps prevent different materials from becoming mixed and makes the later sorting process more efficient. Depending on the size of the aircraft, the cutting process may involve diamond wire saws, industrial bandsaws, hydraulic cutters, or large metal shears. Aluminum alloy panels stretching tens of meters are gradually divided into smaller sections, while components made from titanium, steel, and composite materials are separated individually. A modern aircraft is not built from a single material. Aerospace-grade aluminum, titanium, and carbon fiber composites each have different recovery values and require different treatment methods. The goal of this stage is not to dismantle the aircraft as quickly as possible, but to recover the maximum amount of each material at the highest possible quality before it enters the recycling process. After the fuselage, wings, and tail have been separated, excavators fitted with hydraulic shears begin gripping, crushing, and tearing the massive structures into smaller pieces. The immense cutting force allows the blades to slice through alloy skin, reinforced frames, and thousands of rivets that once held the aircraft together through tens of thousands of flights. This tearing process does more than reduce the aircraft's size. It also exposes electrical wiring, steel, copper, and other components trapped between multiple structural layers, allowing them to be sorted more accurately later. In an Airbus A320, approximately 72% of the airframe consists of aluminum and aluminum-lithium alloys, alongside around 9% steel and 6% titanium. The more completely these materials are separated at this stage, the greater their recovery value becomes. Within a short period, a fuselage nearly 40 meters long can be transformed into thousands of pieces of scrap. Yet this is not simply a chaotic pile of waste. At modern facilities, around 90 to 92% of an aircraft's total weight can be recovered or recycled. After the fuselage, wings, and tail have been torn into smaller sections, the metal scrap is fed into a shredding line. Here, the original shapes of the aircraft skin, reinforced frames, rivets, and other structural components are completely destroyed in preparation for materials separation. At the heart of the system is a high-speed hammer mill. Heavy steel hammers rotate continuously inside the shredding chamber, striking and tearing the scrap into smaller, more uniform pieces. This process also releases copper wiring, steel, aluminum, and other components still trapped between multiple layers of the aircraft structure. The output size is controlled by screens and an automated feeding system. If the material remains too large, the downstream sorting equipment may struggle to process it. But if it is shredded too finely, aluminum can become mixed with steel, copper, or paint coatings, reducing its purity and recycling value. After this stage, an airframe that once stretched for tens of meters has been reduced to a steady stream of small, uniformly sized scrap. Yet this is not the final product. The mixed material must still pass through magnets, eddy current separators, and other sorting systems to isolate aluminum, steel, copper, and other valuable materials. After the aircraft scrap has been shredded, the mixed material passes through a sorting system designed to recover aluminum, the largest material fraction in many commercial aircraft. First, powerful magnets remove steel and other ferrous metals from the material stream. The remaining material then moves through an eddy current separator. A rapidly rotating magnetic rotor generates a changing magnetic field, causing non-ferrous metals such as aluminum to be repelled from the conveyor, while plastics, rubber, and other non-metallic materials fall along a different trajectory. In this way, thousands of alloy fragments once scattered throughout the fuselage, wings, and reinforced frames are concentrated into a separate aluminum stream. However, aerospace aluminum is not a single uniform material. One aircraft may contain several different alloys combined with copper, magnesium, zinc, or lithium to provide strength and fatigue resistance. For this reason, the recovered aluminum is often inspected further using optical or X-ray sensors to classify it by composition. The more thoroughly steel, copper, paint coatings, and other contaminants are removed, the greater the value of the recovered aluminum. After sorting, the material is compressed into bales or set directly to a smelter, beginning its transformation from the skin of a retired aircraft into raw material for new metal products. Once separated and cleaned, aluminum recovered from the aircraft fuselage is fed into a furnace at approximately 660 degrees Celsius or higher, hot enough to transform the solid alloy fragments into molten metal. During this process, residual paint, grease, and other contaminants rise to the surface as dross and are removed. However, aerospace aluminum cannot simply be melted and poured into a mold. Its alloy composition must first be tested and carefully adjusted by adding precise amounts of magnesium, copper, zinc, or silicon to achieve the required mechanical properties. Even a small imbalance can reduce the recycled metal's strength and corrosion resistance or make it excessively brittle. The molten aluminum is then degassed to remove hydrogen and microscopic gas bubbles that could create internal porosity in the finished product. Samples are also taken directly from the furnace for chemical analysis before the metal is approved for casting. Compared with producing primary aluminum from bauxite ore, recycling aluminum requires only a fraction of the energy. As a result, the skin that once enclosed an aircraft weighing tens of tons can be melted down and returned to industry as new metal stock, instead of becoming waste. Once the alloy composition has been adjusted and the molten metal meets the required specifications, the aluminum is transferred from the furnace to the casting system. Here, the molten metal is poured into large steel molds or continuous casting equipment to form aluminum ingots of uniform size. As the metal cools, a water cooling system helps it solidify gradually from the outside inward. Both the pouring rate and cooling speed must be carefully controlled. If the metal solidifies unevenly, internal porosity, cracks, or inconsistent alloy distribution may develop inside the ingot. Once fully solidified, the ingots are removed from the molds, trimmed to eliminate defective ends, and inspected for surface flaws. Depending on their intended use, they may be formed into ingots, cylindrical billets, or large slabs for further rolling, extrusion, or machining into new products. The material that once forms the outer skin of an aircraft has completed a new life cycle, from thousands of pieces of scrap into uniform aluminum stock, ready to return to industrial production. Once capable of carrying hundreds of passengers across millions of kilometers, the retired aircraft has now completed an entirely different journey. Inspection, engine removal, cabin recovery, structural dismantling, metal separation, and finally, transformation into new aluminum stock. What is truly remarkable is that most of an aircraft's value does not disappear when it stops flying. Its engines may continue operating on another aircraft. Its seats and cabin equipment can be reused, and the tens of tons of alloys contained in its fuselage and wings can return to the manufacturing chain. Instead of ending as scrap, an icon of aviation technology is divided into thousands of valuable resources for its next life cycle. If you enjoy discovering how massive machines are dismantled and reborn, hit the like button, subscribe to the channel, and turn on notifications. See you in the next industrial journey on Factron Process.